Okay, so now let's present our first model, which is the deterministic outcome model. So in this example, we introduce the basic framework of moral hazard problems. So there will be an agent. The agent can choose an action or an effort level, which is A, and we say it is non-negative. Here, it may be easier to interpret action as some kind of effort. So if A is 0, the agent is actually doing nothing. Or if A is positive, that means the agent starts to work or to put some efforts. And then effort is not free. So if the agent wants to work hard, the agent needs to pay a cost for working hard. And the C function is the cost function of the agent. To make the derivation as easy as possible, let's say C of A is just A. To make the derivation easier, you are able to show that if C of A is something else, the basic principle, the basic ideas we can get will be the same. Okay, the action will determine the outcome. So the outcome is Q of A, which is a function of A in a deterministic way. So that means as long as we know what's the value of A, we know how much we can get as the outcome. Q is assumed to be strictly increasing and strictly concave, because when you put more and more efforts, the marginal benefit of those efforts would be decreasing. And then the principal needs to somehow design a compensation plan to compensate the agent for the cost. So let's call the compensation plan as W. Okay, W can be in two formats. If the effort is observable, then W would be denoted as W of Q and A. That means I can pay you according to how much you work and what's the outcome. But if A is unobservable, in that case the W would only be a function of Q, and that means I cannot see how hard you work. What I can do is to compensate you according to the outcome. For example, I don't know whether this salesperson works hard, so I pay him according to the sales outcome. The principal's payoff is Q of A minus W. This is the outcome generated by the salesperson's hard work or the agent's hard work, and that outcome translated to the principal's payoff. But the principal needs to pay something to the agent. Okay, so it's money minus money. When we assume this format, we are saying that the principal is risk neutral. Okay, because all the money, all the monetary values transfers to the principal's payoff. For the agent, there may be two scenarios. If the agent is risk neutral, then again he also only cares about money, the monetary values of his income and outcome. So the payoff would be W minus A. W is the salary, A is the cost. But if the agent is risk averse, then W becomes U of W. Okay, U of W. Your earning need to be put into the utility function. And then $1 does not always mean $1 when you are rich or poor. Okay? U is strictly increasing and strictly concave, so that this shape can represent the fact that the agent is risk averse. And now let's consider a few scenarios. First, let's consider the first best scenario with a risk neutral agent. The risk neutral agent's utility is W minus A, and the first best means that the action is observable. We want to first do this because later we're going to see whether that hidden action creates a problem. So the principal's problem is here. The principal can choose action level, okay, because the effort is observable. So the principal can decide, can write that effort level into the contract. And then the principal can pay the agent according to the hard working and the outcome. So the function would be like this. The agent needs to get this to be non-negative. Okay, this is the agent's payoff, the payment minus the cost. And for this part, this is the benefit and this is the payment to the agent. So the principal wants to make sure that the agent wants to live in a stay in the system and maximize his own expected profit. Okay, to solve this problem, obviously the constraint must be binding, right? So the problem would reduce to just a single dimensional problem with effort level. The optimal effort can be directly solved as as A star, and we know A star satisfies Q prime of A star equals 1. That's the first order condition of the objective function. And then our compensation plan. Okay, you have a lot of freedom, but anyway, all you need to do is to make sure that when the agent takes the efficient effort level, he also gets paid enough to cover his cost. Then he will be willing to stay, right? So all we need to do is to simply compensate the agent the cost of the efficient action. As the action is observable, I first choose the efficient action and then compensate the agent for the cost. Then the agent would be able to work and everything goes to my pocket. And the pie is largest, so I can really maximize my profit. This input-based compensation plan is so powerful. It does not need to contingent on the outcome. It only need to be contingent on the effort. Okay, so it's fine. It's fine. Now let's see whether we can still do it when we cannot control the effort level. In that case, the principal can only design W, and W would just be a function of the outcome. Given W, the agent now solves a problem. The agent will choose an effort level by himself to maximize his own payoff. Okay, this is the amount of money he can earn, and this is the cost. Okay, notice that the agent is going to choose an effort level and knows how much will that effort level transfers to the outcome and how the outcome can be translated into his own payment. Okay, and let's use A to denote the equilibrium choice. Then the principal's issue is that A must result in a payment that is good enough for the agent to stay while maximizing the principal's expected profit. Okay, you can say that this is the IC constraint, this is the IR constraint. Okay, quite similar to our screening scenarios. So now the question is, may the principal still induce the first best effort which satisfies a specific condition? Well, the answer is yes. Even though the principal cannot choose A star directly, there is a way to induce the agent to do that. Okay, I know what is A star. Okay, A star satisfies a certain condition. So I can calculate the Q star. Q star is the outcome under the efficient effort level. Okay, so I can expect that to happen. And then the mechanism is very simple. The principal can shoot the agent as long as the outcome is not Q star. Or more precisely, I can design an output-based compensation plan in this way. So if I see the outcome is something I want, I pay you something that can cover your cost. If I don't see what I want, go die. Okay? So that's the output-based compensation that can induce the efficient effort level. Because once you are observing this, once you as an agent get this compensation plan, all you will do is to choose A star, and then the principal's problem is solved. So whether the action is hidden or not doesn't really matter. Okay, doesn't really matter. Okay, so you say, well, that was because the agent was risk neutral. So how about the risk averse agent? If the agent is risk averse, do we still have that? So let's do another analysis. We're going to say the agent's utility function is u of w minus a. Okay, so now the agent is risk averse. And let's still first consider the first best scenario. In this case, almost everything is the same, except that now we have this u function in the agent's utility function. U would only appear in the agent's side. Okay? For the principal don't really care about A. The principal only care about W, which is the amount of money that the principal pays to the agent. Okay, so you can see these two terms are different. And because of that, even though you know this constraint would be binding at any optimal solution, it's not going to be something that you can directly plug in back or blah blah whatever. But even though you may not be able to find a closed form solution for A star, you still know that, well, there is an optimal action level. Okay, then let's just call A star as an action level. Okay, that is preferred by the principal. Our objective here is to ask whether the hidden action will disallow the principal to implement the optimal action level. Okay, so let's just call A star as some optimal solution of this problem. Okay, A star is the optimal solution solving this problem. We don't know what's A star, but let's say it's A star. Then obviously W can be designed very easily. All we need to do is to make sure that when the agent really takes that optimal action, he gets enough things to cover his cost. Okay? This equation is to make sure that the agent's utility is non-negative for any Q. But actually, you know Q is deterministic on A, so it doesn't really matter. Or write this in another way is that the payment should be just the inverse function of U with respect to A star. Okay, so that if you plug in this into the utility function, you will get U of U inverse A star, which is A star. Okay, you can do this because the function is something you can control. Okay, so this is first best. And now is second best. The principal cannot choose A directly, so the principal choose a function. With that function, the agent thinks about how to maximize his own expected profit for this format. Okay, I choose A decides Q decides the payment, and the payment decides my utility, and I have the cost. Again, the principal need to make sure that the agent will stay and then maximize the principal's expected profit. So now, how may the principal induce the first best effort level? Well, we play the same trick. I know what should be A star, then I know what should be Q star, the expected ideal outcome. Then again, all I need to do is to shoot the agent if the outcome is not good. If the outcome is good, pay you what you need. Otherwise, shoot you. Okay? So the output-based compensation plan is still efficient and optimal. So the two scenarios are either we have a risk-neutral agent or we have a risk-averse agent. Okay? So that's different. But the fact is that the output-based compensation plan can still be efficient because all we need to do is know, okay, if it is first best, what we will do, and then control the first best scenario by setting that our compensation plan is something that if you do that, you're good. Otherwise, go die. Okay? This can happen simply because your compensation plan can be designed in that way, simply because the outcome is 100% predictable. So when the outcome is deterministic, delegation really does not create any problem. Okay, it doesn't really matter whether the agent is risk averse or not, because we can always implement the do it or I shoot you contract. The agent would get a payment that is just enough to cover his cost for taking the first best action. Otherwise, the agent would get a very large penalty, which the agent will try to avoid. Okay, so the agent in equilibrium earns nothing, or which means there is no information rent, even though there is a piece of hidden information, hidden action. It doesn't really help the agent. Okay, it doesn't really help the agent. The principal can always implement the first best with an output-based compensation plan. The principal doesn't need to really monitor the agent's action or effort, whatever, as long as the outcome is deterministic. Because if the outcome is deterministic, it can be used to accurately infer the agent's action. So that's how the principal can play this idea, right? So this motivates us to study the next model in which the outcome is somewhat random. As long as we all agree the outcome is random, then I just cannot shoot you if the outcome is something I don't like, because it's always possible that it is the nature that is playing the random thing. Okay, so that's the topic in the next video. Thank you.